This next test is known as the root test. And what it says is that instead of using the ratio test where you look at the ratio of consecutive terms, try to figure out what the limiting value is, here we look at the nth root of the nth term and try to figure out what its limiting value is. Now I'm just going to flip back to the previous page because I want to focus again on this geometric series. The ratio of consecutive terms, when we looked at it for the geometric series, the ratio was less than 1 when we have convergence. What about the nth root of the nth term? So let's put this in another color. The nth root of an. So here I'm going to look at the nth root of an. An in this case is ar to the n. That's the same as the nth root of a times r. And as n goes to infinity, the nth root of a goes to 1. So the nth root of the nth term goes to r. And probably put magnitude here, because we don't know whether r is positive or negative in this case. So what do we notice? Well, the nth root of the nth term has a limiting value of r. And for the geometric series, we already know that the geometric series converges when r is less than 1. And so what this starts to suggest is maybe this could be a general result, that if we look at the nth root of the nth term for a general series and we get that the nth root of the nth term is going to something that is less than 1, maybe the series can converge in general. Maybe we can learn something from geometric series that can be used to be stated more generally about other series. And that's what the root test is saying. Saying what we can learn from the geometric series is that the nth root of the nth term goes to something less than 1. In fact, the nth root of the nth term is always this constant r for a geometric series, but that's less than 1. And we get the series converges. So what we're going to do is make this general statement then, that if the nth root of the nth term has a limiting value of L, and L is less than 1, then the series converges. Absolutely. If the limiting value is bigger than 1, then the series diverges. And if the limiting value is equal to 1, then we get that the test is inconclusive, much like we had for the ratio test. So the idea is to try to take a series we know something about, the geometric series, try to pull off some properties that those have. This is really about the r value being less than 1 to guarantee convergence, and trying to make general statements that we can apply to other series. And so the root test says, look at the nth root of the nth term and take the limit. So let's look at a few examples. In the first example, we're going to look at the limiting value as n goes to infinity of the nth root of the nth term. And here, the nth term is n to the n over 3 to the 1 plus 2 to the n. And it might be more convenient to think of the nth root as being raise it to the power of 1 over n. And so this becomes the limit as n goes to infinity of n to the n to the power of 1 over n, that's just n, and 3 to the 1 over n plus 2. And now as n goes to infinity, this goes to infinity, this goes to 3 to the 2, so that all goes to 9. And so we get the top's going to infinity, the bottom's going to 9. So the result is that the limit is infinite, and so it's bigger than 1. And so therefore, the series diverges by the root test. So if we want to think about it this way, remember our goal is to try to figure out, are the terms going to 0 and are they going to 0 fast enough? And by fast enough, we mean going to 0 fast enough so that the integral converges. That was the integral test. Or going to 0 fast enough like another series that we know converges. Or going to 0 fast enough so that the ratio of consecutive terms is smaller than 1 in the limit. That was the ratio test. Or is it going to 0 fast enough? Are the terms going to 0 fast enough so that their nth root of the nth term is going to a number less than 1 in the limit? And in this case, we have that the nth root of the nth term is blowing up. It's not going to 1. And so the terms aren't going to 0 fast enough. In fact, they don't even seem to be going to 0 at all. So the series diverges. And in this case, we had it by the root test. Let's look at the next example. Here we're going to look at the limit as n goes to infinity of the nth root of the nth term. And so this becomes in the limit as n goes to infinity of the absolute value of 5n minus 3n cubed over 7n cubed plus 2. And so that's a rational function, degree 3 over degree 3, so the ratio is, the limit of the ratio is 3/7. 3/7 is less than 1. And so by the root test, since the limiting value is less than 1, the series is absolutely convergent. So the series is absolutely convergent by the ratio test. Remember, it's absolutely convergent, meaning the series where you replace everything with the positive corresponding value, right? There's a negative sign in here, so it's possible some of these terms are going to be negative as we sum the series. Well, what we've tested here by taking the absolute value is we didn't care whether the terms were negative or positive. We took the limit of the absolute value of those things under the nth power sign, and we found that the limiting value was less than 1. So we didn't really care about positive or negative values here. So what we actually proved is that the series was absolutely convergent. And of course, if we know it's absolutely convergent, we have that the series where you do consider the signs then has to converge. So being absolutely convergent is much stronger than being convergent. It means that if you don't consider the negative signs coming up in the ANs, then the series converges, regardless of whether they're there or not. So having that the series is absolutely convergent is much stronger than just being able to say it's convergent. So let's look at the last two examples. Now, if we recall, one of them is the alternating harmonic series. This is alternating harmonic. We know that it converges. We've already seen that by the alternating series test. And here's the harmonic series again, and we know that this diverges. Now, we already know these results. But let's see what would happen if we applied the root test. So in the first case, we're looking at the limit as n goes to infinity of the nth root of the nth term. The nth root of the absolute value of the nth term. So this is the limit as n goes to infinity of 1 over n to the power of 1 over n. And this limiting value is 1. You could get that by using logarithms and L'Hopital's rule. So this was a classic example of some of the limits we computed in Calculus 1. So you get a limiting value of 1. If we do the same thing for the harmonic series in D, again we get the same limit because we're looking at the absolute value of the nth term, so it doesn't pay any consideration to the fact that there was a negative sign there or not. And again, so that limit is 1. And of course, we know that the first series already converges and the second series diverges, and so this tells us that having a limiting value of 1 for the nth root of the nth term gives us no information about convergence or divergence of the series, because we have examples where the series converges, and we also have examples where the series diverges. So the root test here is inconclusive. That's it for this section. Thanks for watching.